as programmers, we have a problem. And that's that we have these very strong opinions about topics. We really care deeply about our craft, and yet when we go out and we talk to other people, we find that there's not a lot of agreement. One of these topics that we have, all these topics that we have, they have this one thing in common, and that's no matter how long we talk about them, no matter how long we give arguments for them, it seems that we're never going to solve them. In fact, I think these are interminable debates. These are debates that it doesn't matter what we do, we just won't come to an agreement. One of these topics that leads to these interminable debates is this notion of programming paradigms. You can go on Reddit, you can go on Hacker News, you can go listen to a talk, and you'll find people advocating for one view or another. Maybe they love functional programming or object-oriented programming or imperative programming, and they're telling you about the virtues of these various approaches. Or they don't want to argue for one or the other. They just want to synthesize. They want to tell you, you can have it all. If you just understand that these are for different use cases, it works out. Today, that's not really what we're going to be talking about. We're not going to dive into any of these paradigms, not going to advocate for any of them, nor are we going to synthesize them. Instead, we're going to meta this whole discussion. We're going to take a step back and think about the very concept of a programming paradigm by focusing in on this one word, paradigm. You see, today paradigm kind of seems like a buzzword, but programming paradigms were introduced at a very particular moment. Robert Floyd, in his Turing acceptance speech, introduced this notion of a programming paradigm, and he didn't pull it out of thin air. He was referencing an earlier work by philosopher of science Thomas Kuhn. In his Structure of Scientific Revolutions, he explains that science operates by paradigms changing over time. And so, if we're going to understand our programming paradigms, we have to understand Kuhn's paradigms. And so that's our chief question today. The question is, are programming paradigms Kuhnian paradigms? And I think this is actually a very important question, because if we can understand how our paradigms relate to these works by philosophers, by a philosopher of science, we can understand more about what we do in programming. But I don't want to stop with this question. I want to really ask, what can we learn from philosophy? You see, I'm a big fan of philosophy. My two hobbies are really programming and philosophy, and yet I think there's these great connections that are completely ignored. And so that's what I want to explore today. And so to kind of give you a view of where we're going, let's start with an outline. So today we're going to be talking about Kuhnian paradigms. We're going to look at what Kuhn had to say about these paradigms in science and see how we measure up or don't to them in programming. Next, we're going to kind of make a link between programming and Kuhn in an interesting way through Peter Naur. Peter Naur was a great computer scientist who really cared deeply about philosophy, and I think he really helps us bridge this gap. Maybe in a way he didn't intend, but in a way that I think is useful for our purposes. Then we'll look at some other contributions. You see that there's actually some deep connections between philosophy and programming that are underappreciated. But then finally, we're going to look at the future. We're going to look at least what I hope to see in the future. The connections we can make, things that we can exploit and expand our own understanding of our practice by taking these influences from philosophers and applying them to ourselves. So let's dive in. Thomas Kuhn is a really interesting character because he started as a historian of science and accidentally found himself becoming a philosopher. You see, as he started learning more about the history of science, he found that our view of science was really wrong. You see, we think of science as this march of progress, where we can just add facts on top of facts on top of facts. We do observations in the world, and we get closer and closer to the truth. And that science is really this accumulation of knowledge over time. But when Kuhn looked back at the history, he saw this wasn't really how it worked. Instead of this gradualism that we think of in accumulating knowledge, he saw times of radical change. this kind of punctuated equilibrium where these revolutions continuously occurred throughout our scientific history. And so Kuhn wants to tell us how science really progresses is not by accumulating facts, but by shifting paradigms. The word paradigm today kind of seems like this buzzword, but when Kuhn introduced it, it wasn't used in modern English at all. It was a Latin grammar word. And so Kuhn has a very particular idea of what a paradigm is. It's very rich, it's very involved, but it's this technical term for him. And so let's dive in, try to understand what paradigms are, how they operate in science, and then look how ours start to compare. So what is a paradigm? Well, if you want to have the closest analogy to Kuhn's paradigm that we kind of use today, it's kind of a worldview. It's this belief structure. It's this way of thinking about problems. It tells us what the world is like. It tells us what exists. It tells us what methods we can use to discover new things. It tells us what our standards are, what we're going to accept as evidence. But it also tells us what problems we care about. You see, our scientific endeavors have to be given a direction. They have to have certain problems that we need to solve. But I think more importantly than any of this is that it gives us this shared conception of values. This community of scientists care about the same things. And because they care about the same things, they're working towards the same set of goals in the same way. And once we have this paradigm in place, that's when we can really do science. At least that's what Kuhn argues. And so he tells us, how do we go about changing paradigms over time? Because if this is a worldview, if this is all-encompassing, how is change even possible? And so Kuhn gives us a breakdown. He says that science goes through these phases. And this first phase is this normal science. This incorporates everything that we think of as science today. So for Kuhn, normal science would be, looking at data from the Hubble telescope, trying to find a new vaccine. All of these normal day-to-day activities are normal science, and they operate under a given paradigm. And this paradigm makes intelligible the problems that these people are trying to solve. In fact, Kuhn says normal science is just a problem-solving activity. The problems have already been set for us, and we are trying to go solve them. I think if you want to kind of see this on a larger scale, you can think about the search for the Higgs boson. The search for the Higgs boson wasn't just something that someone randomly decided to do one day. It was something that our theory predicted we ought to find. It told us how we should see evidence for this. And it took us decades and decades to do interesting work, to come up with new experiment design, to come up with new instrumentation, to finally discover this thing. And for the most part, normal science works. But there's times when it doesn't. To think about this, we can go back to the time of Ptolemaic astronomy, where we thought that the world was the center of the universe. This was a normal science activity. This Ptolemaic paradigm ruled, and it actually worked pretty darn well. We might think it's very wrong-headed today, but it was fairly accurate. They could look at the heavenly bodies and predict the locations of them. But as we got more accurate information, as we started looking at the heavenly bodies more closely, we would find that the theory didn't quite work. We would make a prediction, we would observe, and we'd find that the theory told us that this heavenly body should be somewhere it wasn't. And so what do? Well, we bug fix, right? That's the easy answer. Our theory has something wrong, we're just going to fix it. And for the most part, that worked, right? We would fix the bug, and we would then try to make some other observation, we'd find yet another bug, and so we'd fix that, and then that caused some problem over here, and so we fixed that over and over again. And this spaghetti code of a theory starts to come up. And so as this spaghetti code happens, as this theory becomes ugly, becomes unwieldy, people start to lose faith in it. These cracks that have formed in our theory lead to a crisis. And if you look at the time right before Copernicus, it's not like Copernicus came out of nowhere. You can see all sorts of authors writing how they've lost faith in the geocentrism that they believed at the time. That the theory didn't work. That if God made this theory, it was really ugly, and he should have consulted them first. So once we have a crisis, though, what do? You see, these theories still were fairly accurate. They still did scientific work, and so we can't just abandon them. Instead, we need an alternative. And that's the start of the revolution. In the case of Copernicus, of course, it's Copernicus who brought in this revolution. But Kuhn stresses that this revolution is not an easy change. You see strong resistance from these existing scientists who knew their paradigm because they know what it's capable of. In fact, if you look at Galileo defending Copernicus's idea, it's not just, this is the center, look, my math is better. In fact, the math wasn't better. The Copernicus model was not more accurate than the Ptolemaic one. What it did instead was it reconceptualized the way we approach problems. Galileo argues not about the center, but about the very notion of motion. It's a radical departure that promises new ways, new avenues of exploration, and changes the way we think about it. So this is the process of science. This is how science changes over time. But if we're really going to understand this change, what it means to go through a revolution, we have to understand more exactly what that process looks like. And so we're going to break down a paradigm into its parts. We're going to break down how the paradigm changes over time, how it's formed, and what it means in relation to the old paradigm. And when we do that, we'll finally get to see, like, how do programming paradigms measure up? Do we actually have Kuhnian paradigms or not? And so a paradigm starts at a very particular moment by the creation of an exemplar. So for the Ptolemaic to Copernicus, it's Copernicus's model of the solar system. This is the exemplar. This is the signpost. This is the thing that says we can do something different. People look at it and are excited by this prospect. So some examples in science are, Aristotle's physics kind of ushered in a new way of looking at the world. Newton's Principia, Darwin's Origin of Species, Maxwell, Einstein, Lavoisier, all of these different people that we think about as these great scientists who changed our conception of the world around us. They created a work, and that work was seen as a new way that we could do science. Now, to be clear, it didn't solve the problems that we had. In fact, it didn't even solve the problems better than its predecessors in many cases. Newton's Principia only talks about a very narrow subset of what was scientifically understood at the time. But what it does instead is it inspires people. People start saying, I can do things in this new way. And they get on board. And so, what about programming? For our programming paradigms, do we have these exemplars? I think it's clear we do. In object-oriented programming, we have Smalltalk. Smalltalk was incredibly influential in telling us that there's a new way to think about programming. In functional programming, we have Lisp. Lisp was this beautiful marvel. I mean, reading McCarthy's paper, it's really so far ahead of its time. It's so different than what people were doing that inspired a whole new way of programming. It inspired people to look into AI and try to use Lisp as this basis for doing these things. And for imperative programming, we have C. Now, you might disagree with which ones I've chosen here. Maybe you think, oh, no, it's not Smalltalk, it's Java, or Lisp isn't functional programming, Haskell is, right? I don't care which exemplar you happen to believe is the case. I think it's clear that we have these exemplars. But another thought you might be thinking is, well, yeah, someone had to be first. Like, these programming exemplars aren't radical in the way that these scientific ones were. And you're just kind of trying to stretch things. But if we look at, for example, object-oriented programming with Smalltalk, Alan Kay actually tells us very explicitly what he was attempting to do and what he thinks he succeeded in. He says this: it became the exemplar of the new computing, in part because we were actually trying for a qualitative shift in belief structures, a new Kuhnian paradigm. This was very intentional by Kay. Maybe you think he's telling you a lie after the fact, but at the very least, he sees this as being the exemplar. In this new radical way, not just a new way to program, it's a new way to compute, because they're trying for a qualitative shift in belief structures. They were trying to get you to think differently about what you were doing. And it's this qualitative shift in belief structures that leads us into our next crucial element of a paradigm that I think is incredibly important for understanding why we can't seem to agree. And that's this notion that Kuhn calls incommensurability. Now, Kuhn is not very clear on incommensurability, to be honest. A lot of people think he changed his mind later in his life and comes up with some different ideas, but we're not going to be concerned here exactly what Kuhn said. Instead, we're just going to try to understand this notion. And so first we'll start with what it means, quite literally, is having no common measure. So if you try to measure two things against each other, there's no way to do it. And so what does that mean, though, in these terms? Well, there's kind of two senses of incommensurability. There's the first strong sense that Kuhn gives us. That might seem a little radical. And a much weaker sense that I think most people could tend to agree with. So in the strong sense, it says that if we go from one paradigm to another, there's no rational method for us to judge which one's better. He wants to say that if we try to judge between two paradigms, we either take the side of one paradigm and judge the old one by the standards of the new, or vice versa. Or we try to come up with some third-party neutral criteria, and that actually itself forms a paradigm for which we're judging the other ones from. In fact, Kuhn actually puts this in very programmery language that I think is interesting. He says that there's no neutral algorithm for theory choice. I mean, think about it. How could you come up with a neutral algorithm for deciding between two theories that didn't take in some subjective elements about values, about methods? And these are all the things that this paradigm includes. Now, this might seem a little strong. I mean, is it really the case that we have no way of judging between Einstein's relativity and Newton's physics? So maybe Kuhn's being a little strong here, and we need to have something a little weaker. And Kuhn offers us that. He says that incommensurability could also just be difficulties communicating. Right? Today we think that we understand Newton's ideas because they're just approximations of what Einstein told us. But Kuhn points out that this is really to misunderstand the Newtonian. They weren't aiming to be an approximation of anything. They were aiming for the truth. And in fact, it's not really an approximation. See, in Newton, mass is something that's conserved. In Einstein, it's something that's convertible to energy. And when we ignore these differences, they actually matter. We ignore them to our own peril. But it's more radical than just Newton to Einstein. You see, we've kind of looked back at the past of science and just ignored a lot of the details of what went on. So there's actually these very weird entities of our past scientific theories. And these aren't weird Greek terms. These are things post-Enlightenment that we believed, like phlogiston. What is phlogiston? Well, it's the substance that lets things burn. What about corpuscles? I'm really not sure, but I know there was a corpuscular theory of light. So somehow light was made of corpuscles. Caloric is actually the liquid that is heat. So caloric is a liquid that flows from hot bodies to cool bodies. And it is heat. And so you might think that, no, we can communicate no problem with these things. But if we really look at what past scientific theories really said, we'll find that there's real problems here in translation. Well, what about programming paradigms? Do we have these weird entities? Well, of course we do. Monads. Right? If you're trying to translate monads in Haskell to Java, it's a lossy translation. Right? Like, we can try all we want, but ultimately we miss something in the communication. In fact, that's really the monad curse, right? That we can't explain it. But, it's not just monads, right? You have all sorts of different things that we are having trouble translating back and forth, Right? If you grew up only knowing object-oriented programming, when you learn about functional programming, I know I had the question like, how do you even program without objects? Is it just primitive types? Is that all you have? Like, why would you want that? Like, how do you do these higher level things? How do you do inheritance? How do you do dependency injection? Like what are you even talking about? We see these difficulties communicating. But I think it's even more important than that is that we have different values. Functional programmers look at the code and go, side effects everywhere. How can you reason about your code where reasoning means something like algebraic substitutability? And so they judge this code based on their values. Object-oriented programmers might be like, you're not encapsulating state. You're not modeling your domain in any meaningful way. You don't have dependency injection going on. Like, how do you handle the modularity of your code when you've hard-coded so many things like this? And so we really do see this sort of incommensurability going on. And I think this is the reason for these interminable debates that we haven't recognized. But ultimately, I said our question is, are programming paradigms Kuhnian paradigms? In order to answer that, we have to look at the final element, which is progress. You see, science progresses in a way that's unique to it. We don't think of philosophy as progressing. We know that philosophy has changed, we've learned new things, and yet we would say, like, there hasn't been progress in philosophy. Kuhn tells us why. When we say that science progresses, we mean that one paradigm wins. When we look at philosophy instead, there's still Aristotelians to this day. And so, what about our programming paradigms? They haven't won. So, are programming paradigms Kuhnian paradigms? No. Because they don't progress. They don't win out. But maybe there's a better way to understand this. Maybe I've made a mistake somewhere along the way. Maybe we're in a pre-paradigm phase. So Kuhn talks about before a paradigm wins out, there's all these competing schools, and they'll die out once we come up with a better paradigm. That might be the case. If you look at Kuhn, we don't have time to go into it, but he gives us some signals that when we're in a pre-paradigm phase, and I don't think we are, but it could be one answer. Or you could be thinking right now, man, this guy's just obsessed with the word paradigm and jumped into a whole thing in philosophy of science just because someone used the word. But programming isn't even a science. Computer science is the science, not programming. And computer science doesn't take these paradigms as like fundamental. So is there a paradigm in computer science? And I think it's pretty clear there is. In fact, it's called this mathematized computer science by Thomas Petricek. He talks about in his paper, Thinking the Unthinkable, that maybe this is a good thing, maybe it's not. And maybe there's a limit to what we can think because we've adopted this paradigm and we don't question it. But what I think is more important is not really whether Kuhnian paradigms are programming paradigms or vice versa in this case. It's that by reflecting on this, we've become more aware of what we're doing. We understand our programming paradigms more, and Kuhn's breaking down of these elements can help us see why we're stuck in these debates. But if we ended here, I feel it would be a little lackluster. Instead, what we have to do is we have to keep searching. If programming paradigms aren't Kuhnian paradigms, is there anything in programming that is? And I think that this is the more interesting question. And I think that we will find a really interesting answer in a maybe unexpected place. At least for me, I didn't expect to find it. But it's in this work by Peter Naur that's called Programming is Theory Building. And in Programming is Theory Building, Peter Naur tells us what programming is. You see, he thinks that we've mistaken the activity of programming for something that it's not. Namely, the construction of text or executable programs. We think typing at the computer is what programming really is. And he says it's not that. And he has a very particular reason for wanting to explore this, because he says if we misunderstand, if we think programming something it's not, then, to quote him, we will misunderstand the difficulties that arise, and our attempts to overcome them will give rise to conflicts and frustrations. He's not saying that if we just misunderstand, we'll have difficulties. No, he's saying programming is difficult. We're always going to have difficulties, but our fixes are going to be the wrong fixes if we misunderstand what we're doing. And I think we find ourselves in exactly that position, where every time a new method comes along, a new technique comes along, it doesn't seem to fix our problem, and instead just gives rise to conflict. But before we dive in to his theory and what he means, I think it's important to keep in mind a conclusion of his theory, because I want to stress how radical this position is, this view is. Because there's been people like Donald Knuth who will say, I think Naur has great insight, to paraphrase him. I think Naur has great insight, but he's wrong about the conclusion. I find that a very weird form of argument, but we'll ignore that. I assume Knuth does disagree with some of the premises along the way. But let me just show you his conclusion, and I'll quote from him. He says, a main claim of the theory-building view of programming is that an essential part of any program, the theory of it, is something that could not conceivably be expressed, but it is inextricably bound to human beings. When we think of theories, we just think of like a list of laws. Like Newton's law is Newton's theory. But Naur here has a very different notion of theory. And he's taken this notion of theory from a philosopher, Gilbert Ryle. You see, Naur actually in this work cites almost all philosophers. There's very little citations of computer science in this paper. Instead, he even cites Kuhn. But he gets his idea of theory mainly from Gilbert Ryle. And Gilbert Ryle wants to distinguish between the statement of a theory, like listing out some laws, and having a theory. So he puts it this way. He says, to be a Newtonian was not just to say what Newton had said, but also to say and do what Newton would have said and done. So we, after talking about Kuhn, can paraphrase this a little bit differently. To be a Newtonian was to live out the Newtonian paradigm, to adopt the Newtonian way of thinking, to adopt the belief structure of Newton. It was to see Newton as the exemplar and say, I want to do things that way. And so this idea of theory, of having a theory, is to not only be able to tell other people some explanation of the theory, it's to be able to do things. And so Naur tells us that if we have a theory of a program, what can we do? Well, we can make modifications to the program. If someone tells us, like, we're going to change the requirements this way, we can think, how would I change this program so that I can incorporate those requirements? If we are asked a question about, can the program do blank, we can answer it. We are prepared to do a number of different things. We have this knowledge of how to do something, not just facts about it. So Naur is really relying on this knowledge how versus knowledge that. Like, I could tell you all the facts about juggling, but that doesn't mean you can juggle, right? And so this is this notion of theory that Naur has. But how does this relate to Kuhn? I've said that this is living out this paradigm, but how can we find some activity that we do in programming that lines up with what Kuhn talks about in science? Well, I think there's a very direct relation here between rewrites and paradigm shifts. You see, if programming is theory building, then it's part of the normal science activity. When we start on a code base, we are figuring out how this code base relates to the world around us. We are exploring the theory, expanding it, making it more precise in different areas. We are making new predictions. We are understanding more deeply the theory that we have, just as scientists are when they're doing the acts of normal science. And for the most part, this works. But what if the world around us starts changing? What if we start discovering new business avenues that we want to explore? Well, the requirements start changing, and this theory we have that we've embodied in this code base stops being able to account for these new changes. cracks start appearing. As we keep adding feature after feature, a bug starts popping up. Instability happens over here. We can't scale this thing the way that we wanted to. And we start having these cracks form, and we try to fix them, but our code becomes this big mess of spaghetti that doesn't work anymore. And we get to this point of crisis, where as developers, we no longer want to work on this code base. We have lost faith in its ability to handle the world around us. And so what happens? Someone goes off and starts the rewrite. The revolution starts. The exemplar is created. And does the exemplar that starts this infant rewrite, does it solve all our problems? No. But it gives us a signpost. It gives us a new way to think about old things. And so we leave the old theory behind and we start on the rewrite. And we end up going very far with this new rewrite. It has different values. It has different entities. It fundamentally changes the way we think about our problems. And so when we hire somebody on and we shield them from that legacy code base, for a while at least, and they start working on this new code base, they go back to the old world and they are confused. There's this incommensurability between them. There's this shift in values. There's a change in the fundamental entities that we have, and so the words we're using are confused, and there has to be this translation that's lossy between them. See, I think that this is where we actually see Kuhn's paradigms play out. And the only reason we can see this is because Naur helped us see what programming is, and that's this process of theory building. And so I think this is really important. I think that seeing the influences that philosophy can have on us, seeing the way that we can make these connections, helps us become better programmers. And so I want to talk more about these influences. You see, there's actually very deep influences that I don't see taught very much. There's the obvious ones that we'll get to, but we'll take a little different spin on them. So these philosophical influences at the base of what we do, we think of Turing and Church. Of course. But we don't think about why Turing and Church did what they did. It was because of Hilbert's program of meta-mathematics, which is really philosophy of mathematics. See, these were mathematicians reflecting on their own work, thinking about how they did things, and applying them. And they came up with something new and unique that gave birth to programming. Before this, we even have Bertrand Russell, who was reflecting again and trying to do philosophy of mathematics and discovered this real problem, Russell's paradox. And so how did he solve it? Well, today, if you've taken set theory, you might think of ZFC. But that wasn't Russell's solution. Russell's solution was a theory of types that have heavily influenced our notions of type theory today. And then finally, one that's maybe a little less known is this work by Rudolf Carnap in 1934, The Logical Syntax of Language. Here he's trying to explain the syntactical structures of language in a way that if you go read today just reads like a programming text. I mean, his works literally look like Haskell code half the time. It's very interesting, and you can see this influence in early papers by the Rand Corp, for example, on how to have computers answer questions. This very fundamental stuff that we do today. But it goes beyond foundations. There's philosophical influences all over the place that we ignore. Alan Kay tells us that small talk, its objects, are very similar to Leibniz's monads. Now, Leibniz's monads have nothing to do with category theory monads. I'm not going to explain them, but this connection might help us understand what objects should be more. We use the term referential transparency. This actually comes from Quine, who is a philosopher, and one of the things he's dealing with is this notion of reference. So one problem is, if I said, Santa Claus does not exist, what entity in the world am I referring to say it doesn't exist? Whatever entity I'm referring to, it doesn't exist, so I'm referring to nothing. So this sentence seems meaningless. This is a problem in philosophy. And so referential transparency is when we can clearly see what we're referring to. If I say that person over there, you can look and see who I'm referring to. If I say the tallest person in Indiana, you probably don't know who that is. It's not transparent. Then there's works where there's this incorporation of things like modal logic into programming. So Joseph Halpern has done some great work. There's other authors here as well, but I just call it Joseph Halpern for like reasoning about knowledge, where he applies modal logic to distributed systems. And so that we can think about distributed systems applying this framework of modal logic to them. And then finally, my favorite, because it's the best name for a programming language ever, is the programming language by John McCarthy, Elephant 2000. So Elephant 2000 was John McCarthy's like aspirational idea of what programming in the year 2000 would be like. Back when that was a cool thing to think about. What would this in the year 2000 be like? And he knew we weren't going to get there. But in this paper, he talks about programming with speech acts. Now, speech acts are a philosophical concept from John Searle and J.L. Austin, primarily, that talk about when we can speak in the world and cause something to be. So an example of a speech act is a promise, right? So a promise, if I say, I promise you that I will do X, I have now made it true, given certain circumstances, that I have an obligation to you to do X. And so these speech acts were things that can make direct effects in the world. And it seems like this is just like fallen by the wayside and we never talk about it. But it's actually been revitalized in Brett Victor's Dynamic Land, where they want to make this very direct connection between the programmer and the world. And so they use speech acts, wish and claim, to actually make effects in the world using a program. But we can't just stop with what has influenced us. I want to suggest ways that we can explore further. I want to suggest things that I find interesting that I would love to see people explore more of these connections and help us understand this better. So the first seems a little far afield, actually. It's in the philosophy of art history. This is this work by Michael Baxandall, Patterns of Intention. And in this, Michael Baxandall tells us how we can do histories of artifacts. He ultimately wants to tell us about art, but he actually starts with an engineering artifact, the Fourth Bridge. And in this, he traces these intentions that went into the creation of the Fourth Bridge to help us understand its history better. And we do this all the time in our programming practice. We dive into Git, and we go look at Git commits, we look at comments, we look at code, who changed it, which author, so that we can understand the intentions behind this code, so that we can make sure that our change makes sense. But is there any writings or thoughts about what are we doing here? We can't really know the thoughts of the person. How do we do this historical investigation? And Michael Baxandall tells us. And so this can be something that we can be influenced by and write about. We can look at historical methodology and understand our practice better. This might seem a little far afield, and this next one might be a little bit closer to home. So there's this topic that's pretty hot right now in the philosophical world called conceptual engineering. And in conceptual engineering, we're asking about our concepts or our words, depends on the philosopher. We're asking about our concepts, and we're asking what they should mean. And so we're kind of come up with new words or change the meaning of old words for some purpose. So a great example that's always given is the coining of the word genocide. See, there was this phenomenon out in the world, genocide, that we didn't have a word for. But by giving it a name, by giving it a word, we can draw attention to the phenomenon and we can make social change. And this idea of conceptual engineering is used by philosophers of gender, philosophers of race, to really try to affect change in the world. But it's also used as a technical device. So there's this idea called supervenience, which we won't get into, but it's used in philosophy of mind, philosophy of ethics, all sorts of things. And having this notion of supervenience helped us understand problems better. But David Chalmers notes that talking about engineering concepts seems weird. Concepts aren't concrete objects. They're abstract objects. How can you engineer something that's abstract? And he actually points to us, software engineers, as people who engineer abstract objects all the time. And you can see this in our own practice. MVC is a great example of conceptual engineering, where we changed words and said that they ought to mean certain things for certain ends. And so I think we could contribute to this work of conceptual engineering, but we can also learn from it and apply it more readily to our practice and realize that we're doing this all the time. But then finally, I think that there's projects that we should just have because we care about them. It doesn't have to be necessarily applicable to the broader philosophical world, or that the broader philosophical world has already given us the answers, because they haven't. And that's a philosophical exploration of the notion of abstraction. You see, abstraction, I think many people would agree, is fundamental to programming. And yet, where's our comprehensive work? We have some folk knowledge, we have some truisms like abstraction is information hiding, or we can distinguish between abstraction by parameterization versus abstraction by naming. But we use abstraction so much. We talk about more abstract, less abstract. And maybe these terms are just purely subjective, but I think that there might be some way that we can help understand more systematically what we mean by these ideas. So here's two works that I think are useful as a starting point for this. The first is this idea of implementation as semantic interpretation. So here, abstraction is left ill-defined, but implementation is defined as an interpretation. So a musical score is an abstraction, and the interpretation of that piece is the performance. And that's the implementation of the score. And so this is at least a starting point for us to jump into. And then there's this work by Karen Bennett called Making Things Up that explains this notion of fundamentality and what things build other things. And I think she gives some really interesting, wonderful criteria that might be useful for thinking about more and less abstract. She doesn't apply it there, but I think that there's a lot that we could gain from her work. But ultimately, my suggestions aren't what matter. You see, I really deeply care about philosophy, and I think it's gotten a bad rep. And a lot of it's for its own fault. Right? When people think about philosophy, they think about this esoteria. They think about things that they can't understand. But there's this school of philosophy called analytic philosophy that actually was given birth to at the exact same time as computer science. In fact, we are related to them very directly. And if you look at the works that these analytic philosophers have produced, they are very similar to what we talk about. And so what I hope is that whether you agreed with what I said, but especially if you disagreed with what I said, I want you to go out and explore this further. I want to see philosophy have a greater influence on programming and programming have a greater influence on philosophy. I want us to connect these things together, go write about them, give talks about them. I want to learn from all of the people who can explore these things at a greater depth than I can. So that's what I hope that people get out of this talks. Go look into philosophy, go reflect on our practices, and apply them. Thank you very much.